In this video, we're going to talk about alkynes. So we're still dealing with unsaturated hydrocarbons, and now notice that our letter change is a Y. So we had alkanes that were single bonds, alkenes that were double bonds, and now we'll have alkynes, which are going to be carbon-carbon triple bonds. So somewhere in our molecule, we will have that triple bond. We'll talk about the general formula, how to name alkynes, talk about isomers, as well as the physical and chemical properties. So alkynes are going to be acyclic. So again, we're talking about the chained carbons. We're still unsaturated. And in this case specifically, we're looking at carbon-carbon triple bonds. So somewhere in that molecule, we have the triple bond functional group. Whenever we name these, which we'll get into more details in a minute, our ending is going to be YNE. And for alkynes, the general formula is CnH2n minus 2. So again, as just a quick review, we had alkanes, which were the CnH2n plus 2, alkenes, which were CnH2n, and alkynes, which were CnH2n minus 2. So we're going from plus 2 to plus 0 to minus 2. Each time we're losing 2 hydrogens. So here's a couple examples. We've got C2H2 and C3H4. So both of those fit that general formula. We've got 2 times 2 minus 2 is equal to 2. And we have 3 times 2 minus 2 equal to 4. For naming alkynes, we're going to have a very similar set of rules as we did for alkenes, except we're going to change the ending to Y and E to indicate the triple bond. You're still going to have numbering that tells you where the triple bond is, and that number is going to be the lowest number possible, just like with alkenes. The one big difference is that we do not have cis or trans for alkynes, and that is because our triple bond is linear. We have 180 degrees. Whatever's on either side here. So we don't have a top and bottom like we did with the double bond. So remember with double bonds, if you had your groups opposite side, you had trans. If you had your groups on the same side, you had cis. And we don't have top and bottom sides with alkynes because it's linear. So no cis and trans. We will have isomers, constitutional isomers. So we can again have skeletal isomers where our carbons are moving, and positional isomers where the triple bond is changing location. So let's do some practice problems here. We're going to name these alkynes, and then it wouldn't hurt to also practice drawing a couple isomers for at least a few of these. So for the first option, A here, we have a longest carbon chain of 4. And our 2 options for numbering, we could number from left to right or right to left. And notice if we do the blue numbers, our triple bond starts on number 1. If we do the red numbers, our triple bond starts on number 3. So we again want to use the lowest number possible, so we're going to go with the blue option. We also have this CH3 methyl group on carbon 3. So we will start by listing that methyl. So we have 3 methyl. Location of triple bond is on 1. 4 carbons is bute. And now our ending is YNE. If we look at problem B, we have our longest carbon chain here. If we number left to right, we've got 1, 2, 3, 4, 5, 6 carbons total in our chain. If we go the other direction, the red numbers put the triple bond on carbon 5. The blue option puts it on number 1, so 1 definitely wins. We also have these 3 methyl groups to include, so we'll have 4, 4, 5 trimethyl, triple bond is on 1, 6 carbons is hex, and then YNE for the triple bond. Go ahead and pause the video and see if you can name C and D. Alright, for C here, we can number from left to right. Go the other direction. Our options put the triple bond on either number 5 or number 2. So we're going to go with 2. We have an ethyl group to include. So we have 4 ethyl, 2, 7 carbons is hept, ending is YNE. Alright, D, we have a cyclic structure. So just like with alkenes, the double bond, your triple bond is always going to be 1, 2. So we can go either direction. And because there's no substituents on this ring, it doesn't matter. We're going to end up with the same system. So we just need to count our carbons. So we have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons total. So we're going to have cyclo. 10 carbons is dec, and then YNE. Here are a few more problems to practice with naming. So again, I'm going to let you pause the video and work through these on your own first. And also go ahead and try to draw an isomer for this last structure. Do both a positional and a skeletal isomer if possible. Alright, for naming the first one, we number from left to right versus right to left. We have triple bond on 3, and again triple bond on 3. So remember, when you have a tie with numbering the double or triple bond, you break that tie with making the groups the lowest number possible. So the 2 groups we have are these 2 methyl groups. Red puts them on number 5, blue puts them on number 2. So we're going to go with our blue numbers again. So this time we have 2,2 dimethyl. Triple bond is on number 3. 6 carbons is hex. And then the ending is YNE. For the next option, now you could have numbered up this arm and down this arm, or any combination. Either way, you're going to come up with 8 carbons. If we go the other direction, we will find that in both cases, our triple bond starts on number 4. If we look at our groups, we have 2 ethyl groups, and in both cases, we can put those groups on lowest number 3. So both directions give us the same numbering system. So we're going to make sure we use the lowest. So we're going to have 3, 6, diethyl. Triple bond is on number 4. 8 is oct, ending YNE. So 3, 6, diethyl, 4, octine. For this last structure, triple bond is on the end, so hopefully it's pretty clear that we have to start with the 1 there. We have a methyl group on number 3, so 3 methyl, 1 butine. Now I also asked you to draw some isomers. So for a skeletal isomer, we would just need to move a carbon. So right now we've got 4 as our longest chain, with the 5th one branched off. So the easiest thing to do is just put all 5 in a straight chain. And if you drew this as line angle instead of drawing out the structure, that's fine. So this would be a skeletal isomer. For positional, we still have to keep the carbons in the same connectivity. The triple bond was originally here, so we need to ask ourselves, can we put the triple bond in this location? If you count, you've got 1, 2, 3, 4 bonds on this carbon. If we look at this carbon, we've got 1, 2, 3, 4, 5. So that structure does not work. If you try to put it on either of the other spots, you will also find that you end up with 5 bonds to a carbon. So for this particular structure, there is no positional isomer. So it's important to always check to make sure when you move bonds around that you're not exceeding the octet rule on any given carbon. Properties of alkynes are going to be similar as they were to alkenes and alkanes. So they are still insoluble in water. Their densities are still less than water. Boiling points are going to go up as your molecules get longer and bigger, just like they did for the rest. Your smaller alkynes are going to be gases at room temperature, just like we saw with alkenes and alkanes. And if you're looking at hydrocarbons that have the same number of carbons, your alkynes are going to have the highest boiling point out of all three. So the general trend, alkynes are higher than alkanes, which are higher than alkenes. So for each of the following, decide if they're positional isomers, skeletal isomers, or neither. Then determine if the first one has a higher melting point or lower melting point, or the same as the second one that's listed. So the one way to do this is to draw it out, or we can also look for the name similarities like we did with alkenes. If we look at names, we have hex and meth, which gives us a total of 7. The other one we have pent, which is 5, and eth, which is 2, which also gives us 7. So both of these are going to be C7H12. So that means we have some type of isomer. The base name hexyne versus pentyne means that we have a different carbon structure, which means these have to be skeletal. We want to draw these out, hex with the triple bond between 2 and 3 and the methyl on 5 versus pent. Triple bond is on carbon 1 and the ethyl group is on carbon 3. So carbons have to move around to get between these two structures, which makes it skeletal isomers. For the next one, we have heptadiene and 2-heptyne. So 2-heptyne, hept is 7 carbons, so we have C7H12. Heptadiene, we have C7, and because it's a diene, we are at that 2n minus 2 again, so we are at the same formula. The heptadiene we've got a double bond between carbons 1 and 2 and 6 and 7 versus heptyne, triple bond between 2 and 3. So in this case, carbons aren't moving, but we don't have the same functional groups. So we're going from 2 double bonds to a triple bond. So to be positional isomers, the functional groups have to be the same. So this is also considered a skeletal isomer. For the last one, we have 4-methylhexyne. So hex is 6, meth gives us one more, which is 7. The other one we have hex and meth again, so we're C7. So C7H14, H12 for both of these. We have hexyne in both cases and methyl in both cases, so that means that the only thing that's changing here is the position of the triple bond. So that makes this positional. As for the second half of this question, determining which has the higher and lower melting point, for the first one, we have the same number of carbons, but we have more branching in the second one, so it's going to have the lower melting point. So I'm going to circle the highest melting point in each of these. So the first one is higher. For the second option here, we have a triple bond versus double bonds. And on the previous slide, we had triple bonds having the higher melting and boiling points. So that makes 2-heptine higher. Then for the last structure, we have the same formula, same connectivity, same functional group. So here they're going to be the same. For the chemical properties of alkynes, just like with alkenes, I want you to recognize these reactions, but you do not have to write or predict their products. So one of the common reactions that we have with alkynes, again, just like alkenes, are addition reactions. So if we think about having this triple bond, if I get rid of the triple bond and make just a single bond, now these two carbons have room. So if a molecule of HCl comes in, instead of the HCl being bonded, what's going to happen is we'll form a bond between carbon and hydrogen and carbon and chlorine. If we look, we still have room on these carbons to get to 4 bonds. So a second molecule of HCl can come in and add to where the triple bond was. So that's how we get from the alkyne to the product. If we look at, say, the second to last problem here, again, I'm going to get rid of the triple bond. If I bring in this case Br2, we can form bonds to carbon. Both carbons still only have 3. So we can bring in a second Br2, and we have our addition product for the alkyne. Again, all you need to do is recognizing addition from going from the alkyne to the final product alkane.